Hello. You should hear me now. Does that seem okay?
Yep, we can hear you.
And you see the desktop?
Yep.
Okay. So let me get the list of people. Okay. All right. So now let's see. What we're going to do today is pick up where we left off on Tuesday. We were talking about binary trees. So I'm going to download the zip file and I'm going to do some more examples from this zip file. I put some new reading assignments up there. Okay. So real quick, there's this reading assignment about binary trees, and you don't need to read the part about sort trees. We're not interested in binary sort trees. We're interested really in binary trees and expression trees. Okay, that's what we're really interested in. And then here's another reading about binary trees from another data structures textbook. Okay, and like the other one, read the first couple sections. So it's pages 145 to 159, about 15 pages of this. So read about 15 pages, and it talks about, it's actually pretty well written, I think. It talks about binary trees and tree traversals and a little bit about expression trees. And then you stop when it gets to the stuff about sorting trees, because a lot of people, sorting trees are real important in other courses, not in this course, but this one also goes into binary sorting trees. So just read the first 15 pages of this chapter on binary trees, okay? And then here's something that's a little bit interesting. This is an older book. The guy who wrote it makes it available for free, and he's actually rewritten his book as an interactive online textbook. And here's a link to the interactive version of the book. And I actually didn't even know this was up there. I found it last night. I didn't realize he had rewritten the book in an interactive way. And what that means is this is written in JavaScript, and there's animations, and you can do exercises online. It's kind of like trying to be something a lot more interesting, a lot more new. Okay, so some of the pages have JavaScript animations built into them. A lot more pictures, some different kinds of animations like this. Here's an animation you can step through. So they're trying to explain things in a more graphic, more modern way. So you might want to read that too. Okay, so that's the more modern version of the old-fashioned book. The old-fashioned book was just a PDF document, and actually that old book it was sold in a bookstore also. The older version is a book was sold as a textbook. This one strictly exists as an online thing, and it's kind of interesting. All right, so the thing is to find resources that help you understand binary trees. If you read one of these and you feel you understand everything you need to know about binary trees, you don't have to read all of these. But if as you're the homework assignment hasn't been put up there yet, but when you get to the homework assignment, you'll have a better sense of what you might need to read when you see the homework assignment, and when you see exactly what it is you have to write. Okay, but so there's two good resources about binary trees: this online book, this older version of a book, and then this newer version of it. So these two are very similar. This one's just a rewriting of this one. Okay. Oh, and this is the website this is the older book. That's what the cover looked like. Okay. And like you said, that book is from it's actually not that old. It's from 2013. Okay. But then this is the new book. Okay. And it's got a lot in it. We're interested in the part on binary trees, which is this chapter 7. Okay. And actually, you see, it's a very long chapter on binary trees. We're only really interested in it up to, I don't know, up to about here, about half the chapter. See, here it starts binary search trees. We don't need search trees. Okay. Search trees are needed when people study things like databases and things like that. Machine learning, artificial intelligence, databases, they make a lot of use of search trees. Programming languages make use of these expression trees. So we need essentially just the first half of this chapter on binary trees. Though if you're interested in things like big data and artificial intelligence and machine learning, you really do need to know about search trees. This stuff on binary search trees is very well done. Okay, all right. And so that's the reading assignment on binary trees, to try to, again, these are data structures textbooks. These are not programming languages textbooks. So what we're doing right now is just making sure that we know enough about the tree data structure to be able to do programming languages. Okay. And let me stop there. Does anybody have any questions about what we talked about on Tuesday? Anything that's come up? Any question about something? Anything? Okay, so let's go back to looking at the code. I'm going to download the zip file. Okay, and okay, I don't need the zip file anymore. Okay. Where is the, and when my computer's acting kind of funny. Oh, the folder opened up on my other monitor. It was buried under a window in my other I double clicked on this folder, and this thing opened up under a window on my other monitor. So Windows is acting real flaky. It popped open this window under a window on the other monitor. Okay, so now I got it back. All right, so here's the contents of this zip file. Okay, I'm going to do something here. I want to change the names of these files here to better. I realized just a little while ago, just for class, that I could give these files better names to explain a little bit what we're doing here. So this is this one's a B-tree example. And then this is the B-tree language example. These two files here are actually about the B-tree language, which we haven't said anything too much about yet. So this file here is a little bit different than these other two, because this file here doesn't actually talk about the B-tree language. It's just about binary trees. And then these two files combine binary trees with the binary tree language. So that's where we blur from just data structures to talking about programming languages. Okay, so this is the example that we were looking at on Tuesday. We're going to do a little bit more with this one. This one's really just about the binary tree. Okay, and if, for example, this file doesn't use this file or this file, or okay, but these other ones do. Okay, so we want to kind of separate what's in this folder, what we need, and we want to separate the binary tree idea from the binary tree language idea. Okay, so that's really going to transition from purely data structures to how data structures and programming languages overlap. Okay, so now this example here, I have to change this name now. Okay, so this is a binary tree example. Okay, now what it does is it wants to build the data structure that represents this binary tree. Okay, so it's got A at the root, a left branch and a right branch. B's got a left branch and a right branch. C only has a right branch. F only has a left branch. G only has a right branch. So this is essentially an empty left branch, and this is an empty right branch. And C has an empty left branch. Okay, and we use the binary tree constructor to build these things. So that was, here's the B tree class. Remember, we've got two constructors in here. One constructor builds a tree with no children, no branches, and the other constructor lets you build a tree with two branches, but you can make either one of these branches or both of them nulls If you make this null and this null, then this constructor does the same thing this constructor does. If you make this null and you make this one not null, then you have a right branch but not a left branch. Okay, so we go back over here. To start this tree, we're going to build a tree with a left and a right branch. Okay, so here's the tree with node A with a left branch and a right branch. Okay, now the left branch is got node B, and it also has a left and a right branch. So there's the left and right branches for the B node. Now the C node only has a right branch. So there's the null in this constructor to represent B tree with a root C, no left branch, but a right branch. Okay. So I have to type this all out. To build this tree, I have to build it. Essentially, I'm building it by hand with a bunch of constructor calls. Notice that there's essentially 1, 2, 3, 4, 5 trees here. Okay. So, well, actually, there's 1, 2, 3, 4, 5, 6, 7, 8 trees here because this is a tree with it. This is also a tree, but it's a tree with no. It's a leaf node, but it's actually a tree that's got no branches. So there's 1, 2, 3, 4, 5, 6, 7. Was it 1, 2, 3, 4, 5, 6, 7, 8? And if you look down here, there's 1, 2, 3, 4, 5, 6, 7, 8 calls to new. See, there's 8 trees being built. Okay, and then there's 3 nulls. There's a null for that branch, there's a null for this branch, and there's a null for this branch. Okay, so every tree has to be instantiated with a constructor creating a tree object. Okay, so big trees are a pain to create. Like if you have to create a really large tree, and you know, in the real world, you know, people using tree data structures, when you could create a tree data structures with hundreds of thousands, even millions of nodes, nobody's going to be able to type this kind of code to create a tree with millions of nodes. We need our goal is to find a better way to build these trees. Okay, and that's where the tree language comes in. You know, this is limited to how big a tree you can build here, because there's just a limit to how much code you can type here to build a tree. Okay, so, and it also becomes very unreadable. Notice, oh, one thing, notice that this is all one line of Java. That's one line of Java, because that's a constructor with a constructor nested in it, with a constructor nested in it, with another constructor nested in that one, with a constructor nested inside of that one, and a constructor nested inside of that one, and a constructor nested inside of that one. This is all one constructor call with a bunch of other constructor calls nested in it. So this is one line of Java. So here it's actually written as just one long line. That line and this line 34 is this all is one line, because it really just is one line of Java. Notice how unreadable that is. You know, nobody can read a line like this, but it's correct Java. You know, we'll see it compile. It's exactly the same thing as this line here, as this code here. It's the equivalent of one line of, it's one statement in the Java language. This many lines of code is technically it's one statement in Java, because there's only one semicolon there. So the statement starts here, ends there, and that's one statement. So here's that one statement on one line, and it's pretty unreadable. And it's not even that easy to read this way either. Okay, so this instantiates a tree data structure that represents that tree. Okay, and then here's just another way to indent the code. Like this is exactly the same thing as this, just indented a slightly different way. Here I did it where every line is a root. So this is on one line, B is on its own line, C is on its own line, D is on its own line, E is on its own line. Okay, so that's this, you know, A, B, C, you know, they're all in their own line. Okay, and even the nulls are on their own line. Sometimes it's a little bit easier they don't need it. You can make it pretty readable without having to put everything on one line. So here this says I have a tree A, and it's got a left branch and a right branch. You can see the indentation lines up. There's A's left branch, there's A's right branch. Okay, notice I'm putting the left branch of A in line with A. It doesn't really need to be on a line below it. If I do this, it's still pretty readable. There's the root, there's beginning of its left branch. Now B has that left branch, and there's B's right branch. So there's B's left and right branch. Okay, I can put the left branch of B in line with B, and it's pretty readable. Okay, now A's right branch starts there. There's A's right branch. Its left branch is null. There's C's right branch. So C's left branch is null, C's right branch is F. F's left branch is G. Oh, my indentation got missed. No, I'm sorry. F's left branch is G. G's left branch is null, and G's right branch is this. And then this is the right branch of F. Okay, so there's F's left branch and right branch. Notice I got it down to what is that? 1, 2, 3, 4, 5, 6 lines. But see, this is 6 lines that are readable. This is a lot of lines that's also readable. This is 1 line that's unreadable. So there's a little, when people write this kind of code, people debate what's the best way to write this kind of code. You're trying to build a data structure using constructors, and it's a little bit messy to do this in Java. Some people write it in a little bit more verbose way than that. Some people like to write it in a little bit more compact way like that. Nobody's going to write it like this. If you just start arbitrarily chopping that line into pieces and just say, oh, well, I'll cut it off there, and I'll cut it off there, and I'll cut it off there, then you end up with just completely unreadable stuff. Nobody can read that. You completely lose the structure. What's A's left branch? What's A's right branch? So the lines are short, but they're unreadable. Indentation is really important to show structure. Okay, so this effectively shows the structure with a lot of lines. This effectively shows the structure with fewer lines. Notice this one needs more indentation, though. This one ends up going a little bit farther out to the right. If you just start, some people could just take an extreme case that every new is on its own line. You'll occasionally see people do something like this, and that's unreadable. You can't begin to tell me what tree that builds. You can't begin to tell me that. Well, okay, you can tell me real quick that A is the root. But where is D in this tree? Where is F in this tree? It's pretty hard to tell. So this is not acceptable code. This is not, in a professional environment, nobody would accept that as a way of describing this tree. Okay, Java lacks a good way to describe data structures like this. Now, not every language is like that. For example, in JavaScript, there's something called JSON. Okay, JSON is a language kind of built into JavaScript. JSON stands for the JavaScript object notation. It's a way of describing objects. It's a language for describing objects. Okay, so now here is what we'll learn. This is the grammar for the language. This is a subset of JavaScript, but it's so useful that it's used by a lot of people outside of JavaScript. JSON has become a way to describe things like tree data structures in other languages. Like you can use JSON now in Java if you want. It's not built into the Java language, but there are libraries that let you use JSON in Java. And JSON is built into JavaScript. And it's a language that lets you write objects in a more compact way. Like this describes an object. Notice there's no new. This line of code in JavaScript builds an object without you having to say things like new object, new object. Call it, you don't have to call all the constructors. You have a little language that describes the structure of an object. Okay, and you can use this to describe pretty complicated objects. You can build trees out of this notation. Okay, so it's a way of describe. Now, in the Java language, this is referred to as an object literal. This says to the JavaScript language, build me this object. Now, if you know the JavaScript language, you know what object that's building. But you don't have to type the word new, 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 new. You just use this syntax, and it builds an object for you. Here's where you have something kind of like that in Java. In Java, if you want an array, you can do int a equals. Now, suppose I want to describe what's in the array. I have a notation that says I want the array to hold 23, 34, 56, and 78. Okay? That's what we call an array literal. Now, what's the alternative to that? The long way would be to say int a equals new int 4. See, that creates the array object. Then you'd have to say A0 is 23, A1. See, the literal saves you from having to write out all this kind of stuff. It would be nice. See, now that's the literal. That's what we want down here. We want something like a literal that says in a compact way how to describe this tree. But Java doesn't have anything like that. You have to write it all out real long way. But for arrays, you do have this one, this here. You can, instead of having to say build the array, then put numbers in it, you have a compact way of saying, here's the array value. Okay. So this is a compact way of writing out, well, this line here is a compact way of writing out all this. Okay. We would like a compact way of writing out all this, something that's easier to read and more compact. Java doesn't have something like that. JavaScript does. You know, this JSON is kind of a way to do that. You can type, notice that the literal here, they look a little bit like the array literals. See how the array literal starts with a brace and ends with a brace? The JSON notation starts with a brace and ends with a brace, and you can use it to describe arrays. In fact, an array is an example of a JSON object in JavaScript, but you can also describe more elaborate data structures than just arrays. So the JSON notation in JavaScript includes the array notation. It includes this, but it includes a lot more. There's a lot more you can say in JavaScript with this brace notation. Okay. Now, so some programming languages have these data structure literals. Okay. Java doesn't. Java, other than the array notation, Java doesn't really have any literals to describe objects, which is unfortunate. Okay, that's one of the little minor disappointments in the Java language, that they didn't give it much power and ability to be able to write literals. The array literal is about the only one there is. Okay, and our tree language is going to be what we do to try to solve this problem. When we start talking about the tree language, essentially we're going to build like a baby version of JSON into our, we're going to write our own code that kind of gives us like a baby version of JSON in Java, something that lets us describe trees in a compact way without having to call new over here. Okay, all right. So let me comment that out. Okay, so really bad way to instantiate our tree, not a bad way to instantiate our tree. Another way to instantiate our tree, you can argue about whether you think this is more readable or if you think this is more readable. Okay, either one of them is good enough for most people. This one's, of course, terrible. No one can read that, and it wouldn't be acceptable. Okay, so this builds the tree in memory that represents this tree here, this is kind of an abstract representation of the tree. It's saying that, well, there's the root A, and there's a left branch and a right branch. On the left branch, there's a B with a left branch and a right branch. So this is a visual representation of the tree. This is an in-memory data structure that represents the tree. Okay, you have a data structure that holds the letter A, and then it holds two references. Okay, and that reference points at another data structure that holds the letter B, and then two more references. Remember, we drew a bunch of pictures the other day that what we're doing is really describing, let's see. Oh, I didn't put the pictures up on the, let's see. I should put the pictures up on the website. Let me see. Okay, here's the pictures. I forgot to put these pictures up there. They're kind of, you know, this is our notion of what a tree looks like. Remember, we're now writing the code that builds this picture. You know, a tree. Okay, I wish I had two. I wish I had two. Yeah, I wish we could. I wish everybody had two monitors and I could do Zoom on two monitors so I could show you all these things at once. It's kind of tricky. Okay, here's a code. And the code is essentially building this representation of that picture. Okay, every time we call new, we're building one of these objects with three things in it, putting the letter A over here as a string. So this would point to the string A. Then this points to this other tree, and this points to this other tree. Then this tree would be a node that points to the string B, and this thing would be a node that points to the string, this would be E down here. Okay, all right, so this code instantiates in the heap a whole bunch of, actually, notice that it doesn't instantiate one object, it instantiates a whole slew of objects. Okay, so we're building a tree, and we think of the tree as one thing, but in memory, it's actually 1, 2, 3, 4, 5, 6, 7, 8 nodes. And those 8 nodes scattered around the heap are linked together to form this one tree that represents this guy up here. Now you have to really think this way. You know, one of the goals is, I'm beating this to death in a way, because I'm not sure if all of you have actually rarely made yourself think that way. To start thinking in terms of data structures as saying that this thing is a data structure, but it's really a data structure made up of 8 pieces of data structures. This is what we mean by a linked data structure. So it represents a tree, but that tree is all these nodes, okay? And they're linked together to form, actually, oh no, I miscounted. How many objects are there here? Somebody try to count them for me. I miscounted them. How many objects does that line of code create? Start on line 55. How many objects are there?
Looks like 8.
How did you get 8?
I just counted each B tree declaration.
Okay, that's what I did. That's what I did. I said that's wrong. I said, oh, I made a mistake. That's not the right answer. 8's not the right answer.
Is it 11 because the null reference counts?
No, they're not objects.
Isn't 16?
Pardon me?
16 because the terminal nodes are the strings, like the B
string,
and the...
Yeah, I wasn't counting the string objects. See, we have to really start thinking in terms of object-oriented programming and data structures. The strings are objects. Each string is an object over in the heap itself. So line 55 has how many objects? Line 55 instantiates how many objects?
2.
2. One B tree node and one what?
String.
String. And if you wanted to, you could actually type here. Java doesn't force you to write new string when you create a string object, but you're allowed to if you want to. So if I wanted to, I could, Java gives you this little, remember we talked about literals. Well, I should have pointed out that that's another example of a literal that Java lets you cheat with. So up here, I could point out that if normally when you want to create a string, you do the following: string x, or okay, s equal hello world, okay? But that's actually a special thing. You really, the real long way of saying string is string x equals new string, hello. This notation is actually a special case of what we call a string literal, okay? So you can just say string x equals quote hello world. That's a shorthand for being able to say this. Okay, you're instantiating an object that now here it's kind of redundant. This string literal is now wrapped inside of a string constructor. So they don't make, you're not forced to do both of them, but you are constructing an object when you type that. Okay, so there's the, you could type out the constructor if you wanted to. Okay, so this is an example of a string literal, and this is a string constructor, which are not quite the same thing. String literal versus string constructor. Down here, this is an array literal versus an array constructor. An array literal does construct an array object, okay, and it initializes it with data. A string I believe I believe you can actually do this in Java. I think you can do that and create an empty string. I can't remember if that's valid or not, whether you're allowed to create an empty string that way with a string constructor but no parameter. I can't remember if that will construct an empty string or not. Okay, so this is we call this a string literal, we call this a string constructor. You initialize a string constructor with a string literal. Okay, this is an array literal and this is an array constructor. Array constructors give you uninitialized arrays, so the array would have zeros in it. Well, they're initialized with default values. An array constructor gives you an array with default values. An array literal gives you an array with the values you want in it. Why do we have both? Why do we need both? Why do we need both a literal and a constructor? Why can't we just say, oh, get rid of the constructor, use the literal? What if somebody asked you, why do you need both of these? What would be your answer? What's the purpose for having both this and this? What's the purpose of the array literal? Why is it in the language? Why did the designers of the language put that feature into the language? What was their design goal? What do you think?
Is it just faster to create it that way?
Yeah, for what kind of arrays though?
Smaller ones.
Small ones. It makes it very quick, it's a lot nicer to type that than to type that. Okay, so it's a convenience. Why do you have to also have this in the language?
For larger ones.
Yeah, what if I want an array of 4 million? If I had to use array literals, I would have to write a literal with 4 million values in it. And I don't feel like writing 4 million zeros to create an array with 4 million items in it. So notice that this is there to create arbitrary size arrays, but you're stuck with just 0 in the array. This is there to create small arrays where you can decide what values go in it. Here, if you're going to create a big array, you have to create the array in one step, and then usually you'd write a for loop to put value. Like if you want the array to hold random numbers, or if you want the array to hold a certain sequence of numbers, then you'd write a for loop to initialize the array. Okay, but you create a huge array with an array constructor, then you'd write some kind of code to fill it in. For small arrays, you can use the array literal. Okay. For strings, this one almost nobody ever uses it. There's no actual reason for there to be both of these. You know, in a way, they could almost get rid of this one. Well, actually, there is a subtle difference between these two. There is a weird, subtle difference. Let me show you. I'm going to use the Java visualizer. Show you a picture. String 1 is HELLO. String 2 is HELLO. Oh, I know it. Oh, I'm missing a quote there. String 3 is string new string HELLO. Now, remember, the Java visualizer shows you pictures of what things look like. Java visualizer we're going to use this in a few minutes to draw pictures of these trees. It draws you what is in the heap. It shows you what is in the heap. Okay, so oh, I have to go back. This is wrong. The Java visualizer, does anybody know what's wrong? Tell me what's wrong with that picture. Java visualizer by default draws slightly incorrect pictures. And I have to go back to this home page and change a checkbox to make it draw the right picture. Does anybody see what's wrong with that picture?
It doesn't separate the strings as an array.
They're not. No, that's not the problem. Yeah, a string is an array. A string is an array of characters. I'm not sure that. Yeah, it doesn't show you as an array of characters, but that's not the real problem here. A string really is an array of characters. But no, there's something a little bit. There's
S1 equals hello with quotes around it, but the quotes are just how you tell it that it's a string. So that's the problem.
That's not. No, every debugger, every IDE in the world will show you the string with the quotes around it. Unless
it's not showing them as references.
Pardon me?
Right.
It's not showing them as references to strings.
Yes, that's the real problem. Those are reference variables pointing at objects. Okay, it's showing them as if they were primitive variables, but they're not primitive variables. So I have to go back and I go to options, show strings, not as primitives, essentially. Now watch the difference. Here's what's really going on. This is a reference variable pointing at a string object. Okay, the string object's in the heap, the reference variable's in the stack. Okay. Ah, look at that. What did it do?
They point at the same object.
Yeah, they recycle strings. Java by default keeps track of strings and recycles them. But look at this. Now, what's
unique?
Pardon me?
It's considered unique to the language.
When you use the new constructor on strings, you always get a new object But if you don't use the new constructor, the compiler will recycle a previous string that has the same value. Very subtle difference, but it actually matters in some programming code. Okay, so the literals get recycled. So this literal and this literal are the same object. When I use the new string constructor, I actually get a new object. Okay, and that's just a weird quirk of the Java language. I actually don't know why they made this design choice. I've never quite figured out why they do this. Okay, now if I go down here and say string S4 equals another one. Oh, see, that one recycled that one. See? Now, they didn't recycle this one. They recycled the literal.
I have a question
Uh-huh.
about, so now that you initialized them all to hello and they're referencing the same, I guess the same variable.
No, they're referencing an object.
The same object. If you go later on to change the variable, would that interfere or would you get an error?
Well, let's try it. When I was in grad school, I had a professor who claimed that computer science was an experimental science like physics. Because every time he asked a question, he'd say, go do an experiment. Okay. And the idea was, the visualizer's goofed up on me. It's hung. Okay. So when the visualizer hangs, you have to reload the page, but then you lose your code. So I saved the code and I can paste it back in. The visualizer every once in a while hangs on you. Okay. So the idea is that if you have a question, what you should think of, what experiment do I do to test my question? So okay, now what was the question exactly?
So if let's say that now that you have them all initialized, down in the code you set, like, let's say S1 to hello with a capital H.
Okay.
Does it change it later on, or do you get an error?
So string, oh, I'm sorry. So now I'm going to go and say S1 equals this different string, right?
Right.
Okay, well, let's see what happens. Okay, S1 points to that guy, S2 points to that guy, S3 has his own guy. Now, S4 is that guy again. It created a new object and pointed S1 at it because it's a variable. See, the whole idea of variables is you can change them. Okay, so S1 stopped pointing at that string object, and S1's pointing at that string object because you told it to. You told S1 to point at a different string object. Okay.
Okay.
So no, one real important thing is, I love the Java visualizer because it lets you try things out real fast. You don't have to create files and bring up IDEs and configure projects. You can just type code and then see it work and see a picture of it. And let me show you a cute trick you can do with the Java visualizer. If you want, well, you can always copy and paste that code into a file. But here's one thing that's really interesting. You click on Generate URL, and then you can take that URL. What I did is I click Generate URL. I put my cursor in there. Control A highlights all of it. Control X copies it. I cut it out. Okay. I can go over here and I can create a shortcut. And I paste into that shortcut. And Java code. Double click on that shortcut, and your code's back in Java Visualizer. Your code is stored in this shortcut. And if you double click on the shortcut, it comes up in the Java Visualizer with your code in it. So you can actually, but let's see, I must not have highlighted it correctly. I lost some of the code. Oh, I know. Actually, the way I created that shortcut's the wrong way to create the shortcut. Windows has got so many stupid little bugs in it. There's actually a better way to create the shortcut. Watch, because what happened was that shortcut tool in Windows is broken. So here's the better way to do this. If I want to save this code, I go down here, generate URL, cut that out, drag this over to here and create a shortcut that way. Then properties, delete what's in the shortcut, paste what's in your, and then it works. See, there's my code. Okay, it's a little bit clunky, but it's kind of cute because you can actually send shortcuts to people. You can email. These act like snippets, like a paste bin, and you can send people, snippets of code in the Java Visualizer by generating a URL. You could just take that URL and paste it into an email message too. So you could just take that URL and paste it into an email or anything, and you could send code to people that way, little snippets of code. Okay, the visualizer is real powerful. It's really useful. It's really useful for understanding how things work. We're going to use it in a minute to look at, it'll draw these pictures for us of binary trees. The binary tree in the heap picture, not this picture, the abstract picture, but the binary tree as a bunch of stuff in the heap picture. We'll see that in a second. The Java Visualizer will do that for us. Okay. All right. So, back over. Let's see. Now, back over to our code. We've been, we were talking about literals. Okay. We have, string literals, array literals. We do not have tree literals. JavaScript does. Some languages do have a way of expressing a complicated data structure in a way that's better than just saying, build the root, build the left node, build the right node, build the left node, build the right node. This is pretty verbose. And this is not even a big tree. That's a pretty little tree. Okay. Now, let's see. I don't need that string constructor in there. I just put that in there to show you. That's getting a little too verbose. You don't need, you rarely have a reason to wrap a string in a string constructor. I mean, like here, the only reason you might is if you want to make sure you had a separate object. Remember, these get shared. This one's a separate object. So that might be the only reason you would ever use new string. But believe me, it doesn't really matter. The reason Java shares these objects is because it doesn't matter. There would be really no good reason for you to need that string to be a separate object in the heap. I'm not even sure why Java does it this way, because it's not useful. As far as I know, I've never seen a use for this. I know what it does, but I've never seen anybody use it in a reasonable way. Okay. All right. Now, once we have the tree built, we can do things to the tree. Okay. So, for example, I can print the tree out. Now, if I go look at the tree code, we have methods in the tree. So, for example, you can ask a tree, how deep are you? You can ask a tree, how many nodes are in you? And you can ask a tree to print itself as a string. Okay. So, for example, this line of code here prints the tree. Now, what that really does is Java by default calls toString for you on that tree. Since you're concatenating the variable with a string, Java calls toString for you. You don't have to call it yourself. So this is calling the toString method on that variable, and it's going over to here, and it's going to convert this, excuse me, it's going to convert the tree to a string. Okay, and what it's going to do is, if the tree has no left and right node, then it's going to, okay, first it creates an empty string. See, okay, it creates an empty string. If there's no left node and no right node, the return value is just the element tacked onto that string. So you just return the root because there's no left and right branch. Okay, now if there is either a left or a right branch, you have to build something more elaborate. Okay, so you take the left, you write a left parentheses, and then the root, And then if there's a left tree, you call toString on the left tree recursively to let the left tree add itself to the string. Now, if the left tree is null, we put a pair of empty parentheses in the output to represent an empty tree. Then we check if the right tree is null. If the right tree is not null, we tell it recursively convert yourself to a string. Okay, that gets tacked on to what we have so far. But if the right tree is null, we tack on an empty bracket. Okay, let's go over and see how that looks like in the output. Like, how is this tree going to look when we print it? Okay, so let me compile that. Oh, let's see. I was playing. Oh, I accidentally tapped something on the keyboard. Okay, there's that tree written out by the toString method. Okay. Okay. Kind of follow along. There's an A, that's the root. A has this left branch, which is a B with a D on the left and an E on the right. That right parentheses closes the left branch of A. So there's the left branch of A. That's how it would be written out. Root B, left branch D, right branch E. Okay, so that's A in his left branch. Now, after you print A in his left branch, you start A's right branch. Okay, so we want to print A's right branch. Well, C is A's right branch. C has an empty left branch. So there's the thing that says that C's left branch is empty. Then C's right branch begins with an F. Okay, now F's left branch begins with a G, and G's left branch is empty, and H is G's right branch. So there's the left branch of F. Okay, there is the left branch of F, and the right branch of F is this empty thing here. See, that's the F had no right branch. And then these parentheses at the end are just closing, they're closing F, C, and A. See, those last three parentheses, they close F, C, and A. So you get a bunch of nested parentheses. Okay, so that's pretty. Now, this is actually our tree language. Our tree, when we start talking about the tree language, what we just did was we translated our tree data structure to the tree language. What we really want to do, the hard work is going to be taking the tree language and having it build a tree data structure. So we're going to have, if you give me a tree data structure, I can print it out in the tree language. And the hard part is, if you give me a string in the tree language, I should be able to build a data structure. That's the thing like JSON. And that's going to be the next example we get to in a couple minutes, where I'm going to start with the string that looks like this. And from that string, I want to build the tree. Okay. Now, here's another way to print out the tree that's a little bit more visual. It's a little bit closer to this thing on the left. It says that A is the root, and B is its left branch, and C is its right branch. So it prints the left, the left branch is indented, and the right branch is indented. Then the left branch of B is indented, and the right branch of B is indented. So now this is level 0. The left-hand column is level 0. This is level 1. Level 1 here is B and C. Now here's level 2. Level 2 is D, E, and F. Level 2 is D, E, and F. See, there's level 2. Level 3 is got only G in it. See, there's level 3. 0, 1, 2, 3. Level 3 has got only G in it. And then level 4 has only H in it. So the levels now are going right with indentation. The levels go down in this picture. The levels go to the right in this picture. This is a very common way to draw trees. Let me show you a real cute way that this is used. In the binary tree folder you downloaded from the internet, this folder here, I put a little program in there called tree. This program came from the Linux operating system. This is a port to Windows of a Linux operating system program. And what it does, if I open a command window here and I type tree, it draws my folder as a tree view. Whoops. Tree draws the contents of a folder using a tree view. Okay. So for example, see this reference folder gives me a subtree. See, inside references is more stuff. So that's shown as a subtree of this folder. Okay. Now, like if I create a folder, X, and then inside X, I create a folder.
Isn't there already something built into Windows like this? Because there's never some
I
tree
think
command
there
for Windows.
That's it. What did you say? I didn't hear the last part. What? I'm going to create some subfolders. Now, subfolders are a tree structure. You know, it's ubiquitous to think of folders sitting inside of folders as essentially a tree data structure. Okay, so I have this X, which has two children, Y and Z. And if I go over here, see my tree, X has two subfolders, Y and Z. Z's got two subfolders, A and B. There's my tree data structure shown in the same way that this guy. See? This way of describing a tree is the same way that's used by the tree program in Linux. Okay. Some people like to see it's real convenient to draw folder structures this way to show people that you get a very quick sense of what's inside of what. Okay. Trees are everywhere in computer science, and these different ways of representing trees are all used all over the place. This tree language that we're talking about up here is important in many ways in computer science. This indentation way of showing trees is important. This visual representation of trees this way is important. And the data structure for trees is important. Notice that we have trees in a lot of ways of thinking about trees. A two-dimensional representation this way, a kind of two-dimensional representation this way, a one-dimensional representation is a string this way, a way of and as a data structure, and representing it as a data structure in memory. Okay, so now this representation is created by the toString method in the B tree. Okay, the toString method in B tree created one of those representations. This representation is created by a program called Pretty Printer. Your homework assignment, when I get it up there, is to rewrite this Pretty Printer to make this output a little bit more compact. Remember the difference between this way of writing the constructors and this way of writing the constructors? This pretty printing here is equivalent to this way of writing the constructors. These lines match up with these lines here. Your homework assignment is to pretty print this tree this way, where the lines of the pretty printing line up with these lines of the constructor. Okay, that's going to be your homework assignment. To pretty print the tree this way, instead of pretty printing the tree equivalent to this constructor sequence. Notice that this line here is equivalent more or less to this. Where happened to it? Oh, where did it go? The one long, oh, this one here. The one that was one long line. Essentially this one line thing is equivalent to this guy here. but in a much more readable way. This is readable. This one up here is not readable. When you make this one line, it's not readable, but it really is equivalent to that. It really is equivalent to this guy here. Okay, so these three things here, this is equivalent to the toString method. Okay, this line here is equivalent to the toString method. I wrote that. It's part of B-tree. This one is equivalent to the pretty printer that's in this folder. And your homework assignment is going to be to rewrite pretty printer to print out the tree, something equivalent to this. This tree will be printed out in 1, 2, 3, 4, 5, 6 lines instead of printed out in that many lines. Okay. And all these different representations are important, and constantly going back between all these different representations. Eventually, we get to be comfortable with the one-dimensional representation, this two-dimensional representation, this two-dimensional representation, and the data structure representation. Okay, all right. So the pretty printer, see, when I print it this way, I'm using the toString method in the tree class. Here, I'm calling a separate function, a static function in the pretty printer class that pretty prints the tree. And the word pretty prints is a term of art that people in computer science use. If you Google pretty print, you'll find a lot written about it. Pretty printing is the term we use for formatting data structures in nice ways in text. Okay, it's essentially a way of saying, do a nice job of printing out a complex data structure. Print it in a pretty way. So for years now, this idea of a way to print out a data structure in a way that you can understand it is referred to as pretty printing. Okay, it's huge numbers of papers have been written about this. It's actually not an easy problem. Good pretty printers are not easy to write. Okay, here you notice that you can JSON pretty print. That JSON language, people work hard at making it look nice when it gets printed. So there's someone who's written a JSON pretty printer. Okay, this was an online one. If you type a JSON code in there and click one of these buttons, it'll give you a nice pic. It'll reformat it for you in a pretty way. That's what they mean. They'll reformat. Oh, and when your IDE reformats your code for you, we call that pretty printing. If your indentation's all messed up, most IDEs will re-indent your program in a nice way. Well, that's usually referred to as the pretty printer feature of the IDE. Okay. All right. Now after this tree's been printed one way and essentially pretty printed one way and pretty printed another way, then I call some tree traversal programs. Okay, we'll talk about these a little bit more. They're in the textbook. That's one of the things. After a little while, we'll go back to this and we'll talk about the pre-order, in-order, and post-order traversal of the tree. Okay, so in your reading assignment, let me go back to the reading assignment. That's one of the things that's talked about in the reading assignment. See, tree traversals. That's the in-order, pre-order, post-order traversal. That's this thing here, the tree traversals. And if you look in this other reading assignment, it's in a couple pages, tree traversals. Okay, so that's this section 5.2. See, pre-order traversal, post-order, there's pre-order, post-order, and in-order traversal. So we'll talk about that in a couple days. So I'll give you time to read about it, and then we'll go back and look at it. It's already been written in the code. So the code for the traversals is in this file called traverse. Okay, and we'll go look at that later on. All of these are recursive functions. Everything in here is recursive. These traversals are recursive. The pretty printer is recursive. Over here, the toString method is recursive. See, the toString method calls the toString method, just like the size method called the size method. Remember, why is this naturally recursive? Anybody, practice explaining this. Does anybody remember why was it that if you want to know the size of a tree, if I want to know the size of that tree, how do you explain to somebody why it's obviously recursive? Think about it. Try to explain it to yourself. How is size of this tree recursive?
Well, if you ask for the size of the tree, you have to ask the branches of the tree, how big are you? And then the branches of those tree, how big are you? So you have to recurse your way through the entire tree.
Right. So this node wants to know how big it is. So basically, he just says, how big are you? And how big are you? And I'll add the two numbers up. So when this node wants to know how big he is, he just says, he delegates to his two children, how big are you? How big are you? But then what's he going to do?
The same.
Same thing.
He's going to delegate to his children. How big are you? How big are you? Add up those numbers, report them to this guy. That's what the code does. Okay. How do you find the size of a tree? You ask your left branch, how big are you? You ask your right branch, how big are you? Add up the two numbers. Okay. See, naturally recursive. Okay. And same thing's being done with this toString. When this tree wants to print itself, it basically prints a 3. Then after it prints a 3, it says, you print yourself. So then this guy prints himself next to the 3. Then when this guy's finished printing himself, he says, okay, now you print yourself. Then he gets printed right after his output. So there's the recursion. When you print this tree, the code's a little bit messier, but you're going to add, here's where this tree prints his root. No, I'm sorry. Here's where this tree prints his root. Then after his root, he says, okay, now left guy, you print yourself. Then after that, he says, okay, right guy, you tack yourself on. See, this is being added on to the result. So the result is the root. Then what's added on, see, I'm using plus equal. What's added on to the root is the left side. Then what's added on to the left side is the right side. There's the recursion. So when you ask him to print himself, he prints 3 and then says to him, print yourself. Then when this guy's done printing, he goes to him and says, print yourself. Okay? Everything's recursive. Everything we would want to do in these things is recursive. Okay? Now let's go and look at, got a few minutes left. Let's look at the data structure, this thing. Here's the code that builds the data structure. We kind of drew a picture of it, but let's have the Java visualizer actually draw it for us. So in the folder, the binary tree folder, I've got a link to the Java visualizer. And if you do the properties, the code is right there. It's in a real messy way. There's the code. There's a whole bunch of Java code. It's formatted in a very bizarre way that has to do with the way the Java visualizer works. But there's a Java program buried in that URL. Okay. And if you just double click on this, there's a Java program. There's a brief definition of the B tree class. Okay. So there's a brief definition of B tree. And then there's a program, a main method that instantiates a simple B tree. In fact, it's the same one. I think it's the same one we were using in the other file. Okay. I think it's the same B tree. Is it? Let's see. I can't remember. Did I do the same one? I think I did. Yep. Yeah. Same B tree. Okay. So this is this B tree with an abbreviated B tree class. Notice that I took out of the B tree class the toString and the size. So this is a minimal version of the B tree class. In fact, I don't even think it's actually more, it doesn't even need, it's not even using these, it's only using the constructor. In fact, I could even shorten this by, all I need are the two constructors. Okay, so B tree class, and then instantiate in the main method of B tree. Now let's look at what this looks like. Go to the Java visualizer. Just click on last and the whole program runs. Okay, there's what it looks like in memory. Okay. There's the root node, the A node. The A node's left is the B node. The B node's left is the D node, and he doesn't have any children. The B node's right is the E node, and he doesn't have any children. Okay, go back to A. A's right was down here, the C node. And the C node doesn't have a left, and the C node's right is the F node. The F node's left is the G node. The G node doesn't have any left, but its right is the H node, and the H node's the leaf node. Okay, so there is 1, 2, 3, 4, 5, 6, 7, 8 objects. Now, notice that by default, they draw the strings as if they were, this is why I think they chose to draw the strings as if they were primitives, to make these pictures a little bit less cluttered. Now, if I go back, it really should have looked like this. Go to options, show strings the right way. Now visualize it. Oh, they still didn't draw them the right way. Okay, let me try again. Let me just click all these little, okay, let me click all of those. There. Now see how messy things get? That's what it really looks like in memory. So you can kind of see that maybe they were a little bit wise to default to showing strings like as if they were primitives. Because then otherwise you get, there's a lot of, well, let's count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 objects. That's what we said. There should be 16 objects in memory, but it's a little bit of a royal mess reading it. So you can kind of see that they probably were right to default to drawing the strings as primitives. That just makes the pictures a little bit less cluttered. But at the same time, this is what really is in memory. The heap has now got 16 objects in it. And those 16 objects all together represent one tree data structure. Now, each object is its own little data structure, but all of them together are creating one tree. Okay. So again, if you uncheck these and you go back to the simplified view, it is a little bit easier to to understand it now. And what's interesting is to go back and trace through the code. Now, we can step through the code line by line. What's going to happen here? Like, see, we're building our first node. Okay. Oh, actually, let's read this code really well. Notice one thing that happened. Which node do you think is going to get built first? Remember the tree, here, the tree is that tree there, right? Which node gets built first?
Would it be the A?
You would think so, and of course the easy answer is not the right answer.
So then
A
I'm
is not
imagining
built.
if it's not A, it's probably H because it's got all the dependencies of G, F, C, and A.
Okay. Now, the beauty of the Java visualizer, it's going to tell us real fast which one gets built first. But let's try to see if we can figure it out. You call this constructor. Before you can evaluate that constructor, what do you need before that constructor can be evaluated? See, that's a function call. And what do you need before you can call the function?
The arguments.
The arguments. How many arguments does that constructor have?
2.
Try again.
3, because it's
3,
got
yeah.
the 2 branches and the
Right.
1 data.
Okay, so before you can build this root, you have to build, well, the string, you have to build the string, you have to build this guy, and you have to build this guy. Okay? All right. So let's start building this guy. Before we can build this guy, what do we need to build?
Its arguments.
It's arguments. So let's build this guy. What do we need to build this guy?
It doesn't have anything. So.
Right. So that's the first one built. See, we can build him right away. We want to build this one, but we can't yet. We can't build it because we don't have the arguments. So we need that argument. Well, we can't build that because we don't have its arguments. So we need that argument. Oh, we can build him right away because he doesn't have any more arguments. So D gets built first. Who gets built second?
E,
E. Then who gets built third?
B,
B, because now the arguments for B are done. Who gets built next?
F,
No.
I would say H.
Let's trace through it real carefully. After we build this argument here, then we need the other argument to A, which is C. Now, C doesn't need a left argument, so that's okay, we can skip it. But we need the right argument of C. C needs that left argument. That left argument needs that right argument, so we go to H. So let's see, somebody write it down. The order now is E, D, B, H. Did I do that right? E, no, D, E, B, H. Okay, visualize execution. Forward. Look who we're building first. D. Okay, D got built. E, next. Okay, notice that we've now built a couple. No, we've got D and E built. We're still building B. See, now we're building B. See, we've got D and E built, so now we're building B. So we went D, E, B. See, now we're building B with children D and E. Remember, next one we said should be built would be H. Okay, so this is what this is all about, really understanding what code does. I give you this code, and if I was an interviewer, and they will do this to you, they'll tell me how this code executes. Okay, this is how we do job interviews. This is an example of an algorithms type job interview question. What order are these objects built in? You should be able to tell me what order they're built in. You should be able to read that code and in your head see what it's doing. And that's what we're learning here. We're learning how to really analyze real Java code. You know, not silly little stuff, but hard stuff like this. Okay, we're out of time, but remember the basic idea is you can't call a function until you have all its arguments. So you're going to try to build A, but you can't because you don't have that argument and you don't have that argument. So you have to suspend the building of A and build the arguments. Well, to build that guy, well, you can't yet. You need that argument and that other argument. Here, there's only one argument, D, and you build D right away, and then you build that tree. Then you build that tree. Now you got those two trees. You can finish building B. When you're finished building B, you're still not ready to build A because you got to build C. But to build C, you need that argument. To build F, you need that argument. To build G, you need that argument. So H is the next one built. After H is G. After G is F. After F is C. After C is A. And what we just did is something called an in-order traversal of the tree. The tree is built. Remember I said that in the readings, there's those traversals. We just did a traversal of the tree in what's called, actually we did a post-order traversal of the tree. We just did what's called a post-order traversal of the tree. The tree is built in post-order post-order traversal form. Okay. And then yeah, this is the kind of stuff we're going to talk about more. This is why we're doing this before we go into the programming languages stuff. There's a fair amount of data structures here to talk about. There's a fair amount of really nice, elegant ideas here to talk about. Okay, notice the Java visualizer is really powerful. You know, you can stare at that code a long time before you really figure out what it's doing, but the Java visualizer can just show it to you. You know, but it's still not trivial. You need to think and watch, think and watch, think and watch. This is what it really boils down to. Watching and thinking, seeing it do something, but then asking yourself, why did it do it that order? What's it going to do next? Think and watch, think and watch. Okay, all right. So on Tuesday, when we come back, we're ready to start talking about the tree language. So we've been talking about the tree data structure all this time. We're going to introduce the tree language. Remember, the goal is to try to get this JSON-like thing. The tree language will save us from having to type all this crazy code here to instantiate trees. Instead of having to type all this to instantiate a tree, we'll be able to just type a simple little string like in JSON and then have a program build the tree from that string. The program will build the tree for us from the string. And I'll just show you real quick. There's the string called the build tree program, and it builds the tree from the string. One line of code, 2 lines of code. 1 line of code to describe the tree, 1 line of code to build the tree. That's what we want to get at. And that starts tying programming languages in with trees. Okay, so I'm going to quit here. Remember, Monday's a holiday, but we'll meet again on Tuesday. So, and your homework assignment will be up there pretty soon. You know, like your homework, like I said, your homework assignment is this idea of you rewriting the pretty printer to get this other pretty printed format, something equivalent to this instead of equivalent to this. Okay, and if you have questions, send me emails or come to office hours. Anybody have any last minute question before we quit? Anybody have a question?
Yeah, was there a link to your office hours?
Yeah, it's on the home page for the course. There's the office hour link. It's in Brightspace.
Got it. All right,
It's
thank
right. Yeah. So that link there will open when it's time. You know, at 2:30. That link will get you in the meeting for the office hour. Okay. Okay. And the office hour is just kind of a joint thing. Yeah. Sometimes one person's in there. Sometimes nobody's in there. Sometimes 2 or 3 people are in there. So it's just anybody can join it and leave it anytime they want. Okay. Just like kind of like real office hours. You can join it and leave it anytime you want. Any other question before we leave? Okay. Have a nice weekend, and we'll meet again on Tuesday. Bye.